So for section 3, we're now looking at multiple events taking place. We're calling these independent events that we can find by a couple different ways. So take a look at this first example. Two events taking place on this. So notice that is one difference between what we're doing in this lesson versus the previous two lessons. In the previous two lessons, we were looking at single events. We said what's the probability of selecting one card or tossing a set of dice one time. And those were all singular events. So we're now getting into multiple events, and that's kind of where we get into this idea. So for the first case, if we were going to, for the first event, toss a coin, so either heads or tails, and for the second event, flip the spinner on this thing that you see on the right and see what we land on. So these are the three scenarios that we could get if we do the spinner over here. So what's the probability of getting heads and heads? So two events, we're looking for probability of heads on this and the probability of a heads on this. There's two ways to do this. One is with this tree diagram, and you should definitely look over this tree diagram. There are going to be some great cases where a tree diagram really helps out. So this is one worth looking at. This is one option. I could use a tree diagram where the first level of the tree, so right here, this was my first level of the tree, represents the first event, and the second level represents the second event. So for the first event, I'm going to toss a coin, and it's either going to be heads or tails. And note that would be a 1/2 here and a 1/2 here. For the second event, these are the possible outcomes. So if I were to toss a heads on my coin, this is what could happen next on my second event. I could get a heads or a tails. Down here, if I were to get tails when I toss the coin, this is what could come next. I could either get this, this, or this. And so over here at the right, you're seeing all 6 scenarios that you could possibly get with the two events. And so when they ask the question, the results are the probability of getting heads and heads. Well, just look at this for a minute. There were 2 of those out of the 6, so 2 out of 6. And so that's one way of doing it, is with a tree diagram. Just lay out the sample space. So this is your sample space right here. Lay out the sample space and just add up the winners and create the probability that way. The other way is with the formula, and that's what you're seeing in today's formula that we have right down here with independent events. So if I were to say, what's the probability of flipping the coin and getting heads? Right? Well, flipping the coin and getting heads is 1 out of 2. If we said doing the spinner and landing on heads, well, there's 2 out of the 3 heads on the spinner. So this is my first event. This is my second event. So because they're independent events, I can do this where I just multiply the 2 cases together to get my outcome. Notice I'm getting the same outcome right here as we got by the tree diagram. So either way works. If the events are independent, then this formula works. So in a case like this, where they say, are these events independent? Well, do they fit this formula? Can I multiply the 2 events and get this answer? So in this case, can I do 2/5 times 5/6 and get this answer? This is a little tricky. See that dot right there? That means that my 3 is repeating. So technically this is 0.33333333. So that's where you're seeing the 1/3 right there. And if you do the math, yes, this does equal 1/3. So we would say, yes, those events are independent. But if you compare that to this one right here, if I did 0.6 times 0.7, I do not get 0.4 as my answer. So these are not independent events. A couple examples to go further. So you got multiple choice questions, and they have 4 responses each. So the probability, if I just guess on a question, what's the probability that I get it right? Well, one of those 4 answers is right. So it's a 1 out of 4 chance. What if we just limited it to 2 questions and we said, what's the probability of guessing 2 questions right? So I'm going to answer 2 questions. What's the probability that those are both correct? Well, 1 out of 4 on the first one, 1 out of 4 on the second one. So 1/16 that I would get that right. Notice as you start going a little farther, and this is only on a 5-question multiple choice test, the probability of getting 100% on just pure guessing is next to nothing on a case like this. So If we said probability of getting all of them correct, well, it's a fourth times a fourth times a fourth times a fourth times a fourth, and that's obviously an extremely small chance of something like that happening. On this one here, if we said getting none of the answers correct, well, look at the probability right here. If the probability of getting something correct is 1/4, the probability of getting it incorrect would be 3/4. And so we're saying that on the first question, there's a 3/4 chance that I do not answer it correctly. On the second question, there's a 3/4 chance that I don't answer it correctly. So if we did that for all 5 questions, this is the probability of that happening. In a case like Part C, and I hope you're catching this, this is a huge shortcut for something like Part C. When you say at least one is answered correctly, there's a lot of cases that you would have to figure out to add together in order to come out with this answer. If we said at least one correct, then I'd have to say, well, what's the probability of getting 1 correct? That's 1 out of 4. What's the probability of getting 2 correct? That's 1 out of 16. What about 3 or 4 or 5? And I would have to add all those cases together. And that works, but here's a shortcut. Use the complement event. If we said at least 1 correct, well, the complement of that would be none correct. And so if I just said, well, let's just do the complement and say, what's the probability of getting none correct? Well, here you go. That was a one-step deal. Here's the probability of getting none of them correct. So if I just do 1 minus the complement, I can get my answer that way a lot quicker. Last 2 examples down here. So if A and B are independent events, and this is key. So because they said that A and B are independent, that means, if you look at your formula sheet, that means this is true. That means I can do A times B to get this guy. And so that's really important. So here's how that would work. If we said A and B are independent events, that means I know A is this, I know B is this, and they're asking me to find A or B. This is key. A lot of people miss this on a test, so I'm glad you're watching. If we said A or B, take a look at the formula for A or B. Right? It's A plus B minus A and B. So this needs to get figured out and included. Because they said that these were independent events, this piece of the formula is found by doing this. So I need to do A times B to get this number and then answer the question. So that's what you're seeing in the math. We have A, we have B, and now we're going to subtract A and B, which we just multiply because they were independent events, and that's where we're coming up with this answer. Again, here's one more example with the same formula. In this case, it's saying, again, A and B are independent events. We're going to use the same formula, but in this case, we know that A or B, we know the result is 0.74. So that's going in for the result, A or B. If we plug into the rest of the formula, I have the probability of A plus the probability of B minus A times B. That's what we're getting right here. But it's still done in such a way that I can now get the probability of A by itself to get my answer. And so that's where this answer is coming from. So these are not so bad if you just make use of the formulas for them.